for this really wonderful workshop, bringing together quite diverse communities in numerical relativity, gravitational physics, and computer science and mathematics. After the morning talks, we are switching back to numerical relativity now. And what's hidden behind this somewhat ambiguous title, New Prospects in Numerical Relativity, is not new numerical methods, but new applications of numerical relativity if we want to think about gravity and potentially modified gravity in the strong field regime. Before I continue, let me just emphasize that because we are such a diverse group of people, I did try to keep it light and I did try to make it understandable, but please do interrupt me if I fall into jargon at any point. Okay, so why would we even bother going beyond Einstein's theory? Einstein's equation, general relativity, is a really beautiful theory. It's very elegant, describes astrophysical phenomena pretty well, and we have more and more tests telling us that Einstein's theory seems to be valid. However, if we then go and talk to our friends in cosmology, they will tell us, yeah, wait a minute. We have something that we can observe if we look at the rotation curves of galaxies, which hints at some kind of additional matter that we can't see for the time being because we don't know what it is. Let's just call it dark matter. Then we have this other thing at large scales that drives the expansion of the universe that we also don't fully understand, and because of that we call it dark energy. And both of these hint at, or seems to make it necessary that we either modify Einstein's equations or we think about new types in particle physics. Now, and then I go back to my friends that were here in Damned who do string theory and say, well, wait a second. Also at high energies, there are some problems, and there are theoretical issues that prohibit us to make general relativity a consistent theory of quantum gravity. So, we have some candidates for that, but so we also don't really know what the theory of everything is, right? And what I'm talking about today is essentially taking those ideas, bringing them down, especially coming from the high energy regime, bringing them down to lower energies, and look at the modification or extensions, that's how I prefer to think about it, to Einstein's theory of gravity. And make a connection between those then new ideas to potentially observations by modeling black holes in these extensions of general relativity. So that's the idea. That's kind of the baseline of what I want to talk about today. And the reason for that is that I think now we are at a time where we can actually use the observations of black holes, the detection of gravitational waves, to learn something about these, about the strong field regime of gravity that we couldn't access before. I'm not saying that we are going to see any modifications of GR, but I think even if we want to constrain those, we at least once need to go through the full exercise and say, okay, I have this theory, let's do the calculation, build a waveform, and then let's compare to the data. Because otherwise what we are comparing to is just our prediction of general relativity, which is wonderful, but it's just testing a null hypothesis in some sense. Yeah? So that's kind of the idea behind this whole program. Okay, so what I want to do with you today is, first of all, give you a bit of a status update of where we stand at the moment in terms of gravitational wave detections and what we are looking for in the future. Then the first part is essentially a bit of a recap of Deirdre's talk on Monday. So what are the key ingredients in numerical relativity, even in Einstein's equations, and and how can we possibly extend that? A 2-slide update of what has actually been done so far in the numerical relativity community. So I'm not the only one working on this topic. And the disadvantage of having to do numerical calculations is that you actually have to choose a theory because you have to implement a specific set of equations. I will also talk about a possible reformulation that may allow us to study a broader set of them at the same time. And that's exactly what I will do in this last part, where I will present to you a specific example of a modification to general relativity that involves terms that are curvature squared. And I'll explain more about that when I get there. Okay. Any questions to you? No. Okay. So what have we seen, or better to say, what have we heard so far? We had the first detection of gravitational waves coming from two black holes that had each about 30 solar masses that orbited around each other and merged into a final black hole back in 2015. Here I'm showing you a summary of the first two observation runs done by LIGO, the Laser Interferometer Gravitational Wave Observatory, and in the US, and Virgo, which is a gravitational wave detector in Italy near Pisa. And by the end, or this catalog came out in the end of last year, and what they had seen were 10 signals coming from black hole systems, fairly massive actually, having masses part of the order of 30 or 40 solar masses, which we hadn't really expected before by our astrophysical understanding. So even those detections already revolutionize our understanding of how black holes form, how stars evolve. Not sure whether you can see those other candidates here in pink, not in pink, in violet. So those are black hole candidates that we can actually observe using X-ray astronomy, where essentially we have a stellar mass black hole surrounded by an accretion disk, and because of the matter inflow that then radiates in the X-ray regime, we can actually infer for black hole candidates. And then down here we have neutron stars, mostly seen in the electromagnetic channel, but then we also had this remarkable event in 2017 where we saw the merger of two, or not the merger, the late inspire of two neutron stars in gravitational waves, and shortly after in X-rays, and weeks and months after across the entire electromagnetic spectrum. LIGO and Virgo started running again after undergoing an upgrade in April this year until I think yesterday or the day before yesterday. I think they're supposed to have a break right now. But up to now, since April, there are 32 new candidates in the current observation run. So if you want to check that out, there are a number of websites, the LIGO website itself, or this one by the group in Birmingham, where they list what candidates, or that they have a candidate, and what the likely source is. So whether it's a black hole, or black hole neutron stars, one of the new sources that we hadn't seen before, or binary neutron stars. And you can find information of where the likely distance is, etc. So that's what we have at the moment. That's where we stand today. But that's not the end of the story. So for me, really, that's just the beginning. And here's a bit of a timeline of what I think we can expect in the future. So here is a picture of the LIGO, the LIGO Livingston detector. As I said, they had their first detection back in 2015. We are now essentially here, 2019, in the third observation run. And the expectation is that we will have an entire network of ground-based detectors, LIGO-like detectors, within the next 5 to 10 years. So Kaga, for example, is a detector that is, I think, currently at the in the engineering run, so testing whether the technology works, and will join the network from Japan, which will help us, once all three of them are online, will help us get the localization of the source much more accurately. So and then, again, infer the astrophysical properties, distances, and origin much more accurately. If we look further in the future, we, of course, we can now detect stellar mass black holes or neutron stars, but in the future we want to do that much more accurately. And there are now proposals going on for what we call a third generation detector, so much more accurate ground-based detectors. And there's one project here in Europe, which is called the Einstein Telescope, and in the US, which is called Cosmic Explorer. And here the timeline is probably the 2030s. And that's already fantastic. But what I haven't told you yet is that these sources, so the neutron stars and the black holes, essentially emit gravitational waves that I would call high-frequency regimes. So we're talking about a few hundred hertz. So essentially, my voice is in that frequency regime, as a few hundred hertz. But if we want to learn more about supermassive black holes, we have to go to much lower frequencies, because essentially the frequency is related to the mass, or the inverse of the mass, to some power. So if we want to learn more about supermassive black holes, like the one that's sitting at the center of our Milky Way, or in fact at the center of most galaxies, we have to go to lower frequencies, we have to go to space. And here's an artistic drawing of the Laser Interferometer Space Antenna, or short LISA, which is a now approved project by ESA and NASA to be built, and the plan is to launch LISA in the early 2030s. Okay, so that's what we are looking at. What I'm not mentioning here is actually going to even lower frequencies, where we would use pulsar timing arrays, and essentially using the radio emission from pulsars that arrives at Earth very regularly, and using that as our arm to do a gravitational wave interferometry. But that's essentially what we are looking at on the observational side. And that's beautiful, but what I haven't told you yet is that the detectors are extremely noisy. So noisy, in fact, that you wouldn't hear a signal out of all the noise. Which also means that unless you have a theoretical prediction of what your signal looks like, you won't be able to see it, or even if you can see it, you won't be able to really uniquely interpret it. So that's why we need different methods to model gravitational wave signals. And here I'm just showing you an example of one of my simulations where we have the Newman-Penrose scale-up psi4 that you've seen in Deirdre's talk on Monday, which essentially is a measure for the gravitational wave amplitude, quadrupole mode thereof, and is related to the gravitational wave strain that we actually measure via two time integrations. So I'm showing you that quantity as a function of time. And what I've simulated here are two black holes with the same mass that orbited around each other for about 10 orbits and then merged. Now, when these black holes are still very far apart and they orbit around each other, and we'll remember Newtonian gravity and say, okay, why do they actually spiral in? So what happens is that they dissipate energy in the form of gravitational waves, and that's why they spiral inwards. And when they're very far apart, we can actually use analytic methods called post-Newtonian methods. So it's essentially some expansion in velocity, orbital velocity over c. Now, when our black holes or neutron stars get closer and closer together, of course, that approximation will break down, and we will have to take into account the nonlinear effects predicted even by general relativity. And that's where we need numerical methods. That's the realm of numerical relativity. And here, what you see is that that's also the regime where we really have the strongest gravitational wave signal, where we have a burst of radiation that we want to cover. And then after our two black holes merge, we will have a highly distorted rotating black hole that sheds away all its non-axisymmetric modes. These are called quasi-normal modes. They are ringing down and then settling down to a final Kerr black hole. So that's the last part here that you can usually calculate with perturbation theory. What I like to do to benchmark my code is actually go, we usually go anyway through this whole process, and then I will use this last part as one of my code tests to compare to perturbative calculations. Okay, so how do we actually do this kind of modeling? Now, we've already, as I said, we've already seen that on Monday. So let me just give a brief review of that. And what we usually do, if we are interested in evolving 3 plus 1 dimensional space-time, so 3 dimensions in space, 1 dimension in time, is that we say, okay, let's take Einstein's equations, or let's start before that. Let's take our space-time, 4-dimensional space-time, and let's foliate our space-time in spatial slices that are labeled by some time parameter as illustrated here. So my sigma here is a 3-dimensional spatial Fourier slice, and we have a whole stack of these slices to then make up our space-time. Then if we do that, we can describe our geometry that originally was described by a 4-dimensional metric G with a spatial 3-dimensional metric gamma ij, which lives on or in this slice. And then we define something that's called the lapse function. So that's essentially determining how much time elapses from one slice to the next if we were to follow along the normal vector pointing outwards from that slice. And we have a shift vector, which is usually called beta, which essentially identifies the displacement of my point that I move from one slice to the next as compared to the just normal observer here. Yeah, so these are the key ingredients. And then the last bit that we need is called extrinsic curvature, and that essentially describes how our slice is then embedded in the four-dimensional space-time. So the geometric interpretation is exactly that, and it is defined as a gradient of our normal vector. But in a relatively straightforward calculation, you can see that that extrinsic curvature is related to the time derivative of our three metrics. So in some sense, you can think about the three metric as your coordinates, and then this k is a somewhat not exactly conjugated momentum, but it's associated momentum to that. And up to here, I really just talked about geometry. What can I do with my space-time to bring it in this form? So here I have no input whatsoever of what kind of theory I'm looking at, which means that we can use that kind of approach to most, maybe not to all, but to most extensions of our standard model, be it in gravity or particle physics. Now, to understand the specifics of a theory, we actually have to identify one. And just for the sake of the argument, at the moment I'm sticking to general relativity. We will go beyond that later on. So what we have to do now is take our Einstein's equations. So here we have our Einstein tensor that contains the Ricci tensor and our energy momentum tensor T mu nu. And what we typically do is project out components onto one of these hypersurfaces and perpendicular to it. And what we find is very similar to actually what you find in Maxwell's equations, is that you get a set of constraint equations that are of elliptic type, or we know how to make them elliptic. And typically what we do is just solve them for initial conditions. And then we also get a set of hyperbolic type partial differential equations that then describe the propagation in time of this extrinsic curvature. Now, this is just a one-slide upshot of what we heard in much more detail on Monday, but that's kind of the theoretical structure behind it. We still have to think about how we actually write down this time evolution PDEs to make them what we call well-posed, or a hyperbolic evolution problem. So this is kind of the first item, and before I start implementing anything, I check that property first, because otherwise you may waste a lot of time, as well-posedness and hyperbolicity of your equations is a necessary condition for numerical stability. Yeah, so you really, really want that. But once I'm convinced we have that, and once I've written down my set of equations, we can think about numerical schemes. We've already heard that the traditional ones are maybe a bit, can be improved in the future. But what we typically do is use the method of lines, where we discretize our spatial derivatives in one way and then choose independently of that a time integrator. Traditionally, we still use mostly finite differences or pseudospectral methods, and oftentimes explicit time integrators like the Forza-Runge time integrator. The other ingredient that we need, and you've seen that beautifully in I think, Paul's talk, is what we call adaptive mesh refinement. Because what we need to do is resolve our black hole or our compact object, and let's take that as a key length scale, and let's call that length scale m. Then we also need to be able to capture orbital dynamics, which is about factor 10 of that. So usually we have a radius of 10 m for that. And then we want to do wave extraction. We want to measure our gravitational wave signal, which is usually a few hundred to 1,000 m away. So these are the length scales that we are talking about, and that's why we need these adaptive meshes. And of course, that results in us using high-performance computing, like, for example, the SuperMOOC system in Munich, where I have some computing time. Now, the other item that I wanted to mention is that if you're interested in using a numerical relativity code, or you want to try out some of your methods, then maybe it's a good idea to start looking at some public codes. I think, so it's not, the list is probably not completely conclusive. So I myself use and develop the Einstein toolkit. Then GR is a new code, and Pao just arrived at the right time because he's one of the key developers for the GR code that you've seen in his talk is much more adaptive than some other approaches. Then Zeki Tian has a very nice new approach called NURPy, where he actually has a Python infrastructure or a Jupyter notebook with Python that helps especially new users to generate code using Python. And I don't know, Lee, what's the status for Spectre? Is that already public, or is that still in the works?
So I'm not making those decisions. My understanding is that parts of Spectre are public, and I think they're making things public as soon as they are confident that they will.
Yeah. So that was my understanding as well. So that's why I haven't listed it here, because I didn't know what the status is. But yeah.
Spectre, I know more about, as near as I can tell, they will never release that to anyone.
Yeah.
They allow me to use it, but only on things that they consider boring.
I see. Yeah. So the spec code, which is the spec code, which is one of these pseudo-spectral or these pseudo-spectral codes for black hole binary evolutions, is not public. But Spectre, I think, uses new methods that they're making public. So watch out for that. Yes. I'm really excited to see that. Okay. So, but that's where we are standing in terms of modeling. Do you have any questions about that so far? Yes, Anya.
How complicated are these different templates? Like, could you imagine a low-order, small number of parameters model that could model all templates by perhaps stretching the time, adjusting the heights?
So that's, so the nice thing, especially for black hole templates, is that the mass already scales out. So that's something you can already adjust, or you then identify by looking at the amplitude. But if you look at the parameter space, you would look at different spins, different mass ratios, at least. And there, I think the most coverage is if you have, and for all these cases, the waveform may look slightly different, right? So there's a lot of coverage for comparable masses, so nearly equal mass binaries, low spins. So what's really hard for us to model are very high spins of the black hole. So if you go close to what we call extremality, close to the largest and loud spin, it's very hard to model. If you go to mass ratios that are larger than, say, 1 to 10, it's going to be very, very complicated, and we have to think about new methods on how to do that efficiently and accurately in the future. So what's happening is the following. If you try to get the full waveform, there are two approaches. So one is to say, let's take this post-Newtonian expansion that I mentioned earlier and our numerical relativity waveform, and let's build a phenomenological model in a certain range of the parameter space and try to extrapolate. And then there's another method which essentially is, so it's called effective one-body method, where you use, again, post-Newtonian, but resum it in a particular way. And then you calibrate that for a finite number in the parameter space to go from inspire, merger, and ring down. Does that answer your question? Yeah?
I have some more things I'd like to ask you later.
Okay, yeah.
But he was also asking if you can now doing a lower dimensionality dependence of the template, and we have in this case without reduced order models or things.
Yeah. So that's of course already used, or in development, and we really need that because otherwise, going through an entire template bank and trying to do matched filtering against a particular template is actually quite time-consuming and resource-consuming. So I think I don't know whether they already switched to actually doing this reduced order or fast identification first, and then do it more accurately with a matched filtering approach.
So they are doing so. The detection is with a much sparse.
Exactly.
The construction of templates, their templates are based on reduced order.
Yeah.
So how long does it take to generalize for a specific parameter?
Depends a bit on the parameter. So if you're just talking about the numerical relativity simulation, and let's talk about 10 15 orbits before merger, we are talking about between a week for comparable mass to a month or even several months if you want to have larger separations for one of those simulations, right? So it's
whether there's some mechanism by which you could do the Ford model to certain parameters based on the exact fit with the parameters?
but
Which is currently being done, or do you primarily work with templates and then?
so I think they primarily still work then with. So once you have this quick model, then I think you would still compare to templates, right? But so then that's why I at length discussed these two approaches, because this waveform building is done with number of numerical relativity simulations, and I think currently available we are talking probably about a few hundred by the different groups. So Georgia Tech, for example, SSX, and Rochester. So that depends a lot. So that's what I meant to say. So if you have equal mass or comparable mass and low spins, we have a quite dense coverage of the parameter space. Those are easier to model. If you go to very high spins or very high mass ratios, then the coverage is much lower or even non-existent if we talk about. So I think the highest mass ratio we have from numerical relativity is 1 to 100, done by the Rochester group for about an orbit, and by myself as a PhD student.
We don't have that.
Well, have that in the sense proof of principle. There is
The
one.
error is huge.
I know. And I mean.
They have it, but Luis doesn't believe it.
Right. So what I'm saying is codes have been run. Yeah. But yeah, so I mean, this is for one orbit, and when I was a PhD student a few years ago, we actually looked at head-on collisions for 1 to 100, together with Uli Sperhake, who is based here in Cambridge. But I think that's about it if you think about that mass ratio, right? So we really have to invest more there, especially if we think about these future detectors.
Is there an attempt to do sort of empirical basis function?
Yeah.
To represent the template. not
Yes.
to define it, but
Yes.
Yeah, but I mean, one thing that's important to remember is that they're using this in a match filtering technique. And so what that means is if you're sort of approximately right, but the phase is off, such that, the signal is going up or the template is going down, then that's counterproductive. So the needs of match filtering are very stringent. You absolutely have to, you cannot afford to lose phase.
Any more questions here? Yeah. Okay, so thanks for pointing out those problems, because now I will do something crazy and say, I said in the beginning, we actually want to go beyond general relativity. And there's a whole zoo of ideas of what one could do. I'm focusing here on just a few of them. And now, instead of writing the field equations, I'm writing down the Lagrangian, roughly. So we have our Einstein-Hilbert term here, the Ricci scalar. And you might think about coupling that to a scalar field phi with the kinetic term, maybe some potential. And different choices for these coupling functions carry different names. I colloquially now just call them scalar tensor series. Another class that I'm currently working on is what I would call quadratic gravity, where your extension essentially is, again, a function of a coupling function of a scalar field, either times this particular combination of Riemann squared terms, which is called Gauss-Bonnet term. Then you will see more about that later. And the second one is called dynamical Chern-Simons, where you have what's called the Pointryagin density, so Riemann times the dual Riemann coupled to what I would call an axion field. And you have many, many more down here. There is a CQG focus issue, which was edited by David Rosa, Leo Stein, and myself, based on a conference that we held last year. And we will actually have a new workshop coming up called New Frontiers in Strong Gravity next year, next July in Spain. And if you are interested, you're very welcome to join the discussion that we will have there and see what the latest updates and latest status is in the field. Okay, so the next two slides are really just a summary of what people have already done in the context mostly of these theories and beyond that. So the first question actually goes back to Franz's talk, where you say, okay, what happens if I couple a black hole to a massive scalar field or a massive vector field? And this list, I hope I didn't forget anything, I hope is conclusive. And the idea of this program goes back to the 70s, where you say, okay, what happens if I have a low-frequency bosonic wave? I just throw it at a black hole that's rotating. Then what will happen is that that wave, instead of being absorbed by the black hole, will be amplified. I'm not going to repeat Franz's really beautiful analogy with a spinning wheel and the stone again, but it's a similar effect, so that the wave that comes out is actually amplified. Now, if your field is massive, what you will find is that actually some of these modes can be trapped by our massive potential. And if the frequency of the field is in particular such that the field's Compton wavelength, just kind of the inverse of the frequency times a number, is comparable to the black hole size, then this growing of bosonic fields is particularly fast. So we can, in this regime, grow bosonic condensates, scalar field condensates, or vector field condensates around black holes. Now you may say, okay, that may be interesting in the context of studying nonlinear stability of black holes against massive fields, but does that actually have any practical application? And the interesting, or maybe surprising conclusion is that yes, it may have such an application, because the condition that I just said, Compton wavelength of the field comparable to the black hole size, translates into the following list, that you can form these condensates efficiently around black holes if their mass is very light. And in particular, if you think about the LIGO black holes, so black holes with about 50 solar masses, then you would be able to probe ultralight fields in the range of 10 to the minus 10, 10 to the minus 12 electron volts. That's talking about things like the QCD axion and the axiverse. If you go to supermassive black holes, then we would be able to probe fields that have a mass of about 10 to the minus 20-ish electron volts. And these have been identified as actually quite attractive candidates for dark matter. So that brings us into a situation where we can now try and use black holes and gravitational waves to look for dark matter candidates, or more generically, because this is just testing and probing gravitational interactions, so more generically we can try and look for beyond standard model particles in this kind of mass regime. And here I'm just showing a complementary simulation to what Franz showed us yesterday, on Monday, where Miguel Ziliao and I implemented also the massive vector field. And instead of having a very fine-tuned initial data, we looked at a composite condensate of a vector field, so something much more generic, and starting already with an energy or a mass that carried about a few percent of the original black hole mass. So in some sense, it's like starting at the endpoint of your simulations and trying to see how the field evolves. And even though it may decay over long times, what you can see here, where again I show you the wave form, so psi4 as a measure for the gravitational wave as a function of time, for a black hole that originally had a spin of 0.95, so not actually particularly high, and a bosonic field with a mass parameter of 0.3, which gives you, if you're in this right regime, actually a monochromatic gravitational radiation and additional modulation. That may, if not with LIGO, maybe with future detector, maybe something that you can try and look for. And that's about all I want to say here. Maybe as a last point is that the code that I just mentioned and that Miguel and I developed is part of a more generic library called Canuda, and in particular the Proca code is already part of the Einstein toolkit, so that has undergone revision, and is, if you go and download the latest version, you will find that evolution code there. Okay, so the next question that you may ask is, I'm talking about black holes all the time, but are the black holes predicted by general relativity actually the compact objects describing everything? My bet would be yes, probably. But people are entertaining the idea of, how could that be modified, or can we actually learn something by looking at toy models that are not black holes, but just as compact. And particularly a popular toy model are boson stars, so essentially very compact objects made out of massive scalar fields, usually with some kind of high order potential, like a 5 to the 4 or 5 to the 6 potential, could be real or complex, so there are different variants out there. And I'm just showing you one example here as again, what could be a signature that one might want to look out for, or not seeing that one may put constraints on these kind of toy models, which is maybe just focusing here on the right-hand side, where Thomas Helfer, one of our former PhD students at King's, who's now in Baltimore with Emanuele Berti, looked at head-on collisions of these boson stars, and looking at different, what we call compactness of the star. So what's the radius compared to the mass of the star, and just let them collide head-on. And then on the right-hand side, what the final outcome of that is that the final object is still a boson star. Okay, and now we can see two lines here. So the one in black is actually a collision of two black holes head-on, just for comparison. And then in yellow is a signal that they got from the boson star collisions, where the amplitude of the merger signal was much lower. But what's interesting is that this final star is still oscillating. So I hope you can see that in the back, that there are still regular wiggles, I might call them, long after the merger itself. Okay, yeah, and I'm still in time, right? Yeah, good. Yeah, so that just is as one point of what one might be interested in. Maybe that template comes from a totally different process. Exactly. And at the moment, the situation is that the templates that we have are for compact objects in general relativity, so for black holes or neutron stars, and just assuming general relativity. So these kind of effects are not yet incorporated, and it would be at least interesting to see, to try and look for it, so that we can constrain some of these modifications, right? Yeah, but so that's, I think, exactly the intrinsic problem that we have. So unless we look for a particular feature, we may not find it, at least not with current detectors, because the data is just too noisy. Yeah. Okay. Any other comments, questions at this point? No. And then we have the next question, and that's what I kind of started off with. Is Einstein's general relativity actually the theory of gravity? And again, the reason why we look at modeling those is precisely that question. It's not, well, maybe I should just speak for me. It's not that I'm particularly in love with them, but it's more this philosophy that, okay, let's try to, at least once have a full waveform model, so that we can try and compare against the data and put new constraints. And let's try to focus on that such models, that would hopefully capture general features that arise in different types of theories, because I certainly don't have the time to go theory by theory by theory by theory, but have one that captures the main effects, and then try. Precisely. That's precisely the idea. Yeah. So I'm just listing here. So one of the first questions before even going to the binary problem is, the question of, do we actually form black holes in a particular theory? And here we have very nice work by David Garfinkel, actually from 2007, where you looked at Einstein-Ether theory, which is one of those that I didn't list before, because it's actually a specific one where you don't have the diffeomorphism invariance anymore. So actually now, instead of having space and time and invariant, you pick a particular time frame. So maybe that teaches us something about why general relativity is so special. And then Franz and Justin Ripley did some simulations in Gauss-Bonner gravity that we will see. So not his simulations, but we will see the theory in a moment, just to name a few. And then there has been quite a lot of work on these compact binaries first in scalar tensor theory, because that's kind of the simplest modification that you can think of. And more recently, Masha Okunkova and collaborators from Caltech have done simulations in what's called dynamic Gaussian-Simons. So remember this Riemann times dual Riemann term that I listed earlier. So that's that theory. And my group, so together with Leonardo Gualtieri, Paolo Pani, and Thomas Sotirio, we've looked at this Gauss-Bonne theory where we have Riemann squared kind of terms. Okay, so that's what I will talk about for the rest of the talk. So if there are any other questions now, let me just pause for a second. No? Okay, so why would I actually look at this theory? And this theory is now written as an action. So we have, again, the Einstein-Hilbert term, our Gauss-Bonne invariant, so this kind of particular combination of Riemann squared terms times a coupling function for a scalar field, and the canonical term for the scalar field. And I think there are actually different ways of how you can think about the theory and where it comes from. You can say quite agnostically and say, well, yeah, I mean, if I'm in the strong field regime of gravity, wouldn't I expect higher curvature corrections? And what's a sensible term that I can write down is this Gauss-Bonne invariant, which still leads second-order field equations, and that are do modified our field equations if coupled to a scalar field. You can also talk to your string theory friends who will tell you that actually these kind of theories do appear in the low energy limit of some string theories, and that was shown among others by Nick Mavromatis, who is one of my colleagues in King's. Or you can say, okay, you know, if I write down the most general form of theory of gravity that gives me second-order field equations in d dimensions, I get something that's called Lovelock, where you actually quite naturally do have these kind of Gauss-Bonne terms, and let's then compactify them down to 4 dimensions. Again, you get this kind of coupling for the scalar field. So in this sense, be it the correct theory or not, I think it will give us some insight in what, how black holes or how compact objects behave when we add these kind of higher curvature terms. Okay, so I think I will talk you through the construction a little bit. I know I'm aware of the time, but I do want to get to the numerical simulations that I actually performed. So I think that's what we can do for the next 10 minutes. And if you want to know any more details, I'm happy to talk to you about afterwards. Okay, so getting a bit more formal now, what are the equations of motion that I actually get from this theory? The following. So I still get my Einstein tensor that we've seen before. I get my canonical scalar field energy momentum tensor, which is essentially just a gradient of the scalar field squared. And then I get this extra term here. And this extra term, if I just, so I'm very schematic here, I'm not very accurate, but if I just write down the leading order terms, what I have here, if I choose the right coordinates, some kind of box operator acting on my metric, and then on the right-hand side, I have second derivative of my metric times second derivatives of the scalar field. That's essentially the structure of the equation. And then I have the wave equation for the scalar field, but now sourced by this Gauss-Bonne invariant. Or if you just again look at the leading order structure, we have the wave operator acting on the scalar field, but sourced now by second derivative of the metric squared terms. So having that as full theory, I know Franz and student were very brave to actually evolve that in spherical symmetry, and they found that behaves well, below a certain value for this coupling parameter, but above that it essentially changed structure and became some kind of elliptic or hyperbolic elliptic system. Is that right, Franz? Or yeah, so a kind of mixed type equation. So very elliptic. So which is even worse. So it's not mixed elliptic hyperbolic in the sense of the equations being mixed, but in the regions. Mm. Yeah, so not like that.
One equation is definitely elliptic or it's hyperbolic and it could be coupled. Let's say one equation
Exactly.
was there's an undetermined character. Some region is hyperbolic.
Exactly.
So it's parabolic on some solid line. So what's the elliptic region?
exactly. Yeah, and that's essentially a spherical symmetry, and I'm assuming, expecting that the same will happen if you try and go to 3+1 dimensions. So that brings me back to one of my earlier comments. If I want to evolve field equations on a computer, especially in 3+1, well, if I could wish for something, I would have a Cauchy problem or a well-posed hyperbolic formulation. Given the structure and what Franz just summarized, that's certainly not the case. One of the questions I have for the mathematicians here is, if you've seen these type of equations, can we actually make sense of them as a well-posed initial evolution, as a well-posed evolution PDE in some kind of other sense? Louis is shaking his head. But let me just put it out there as a question. And so, of course, we have to think a bit harder if we want to go through this exercise, what we can now do. And I took kind of the easy way, and I think it's the same approach that Masha Kunkova and collaborators took, to say, okay, wait a second, where did this actually come from? A slide ago, I said, one of the motivations is that some kind of low energy limit of a more fundamental theory. So let's do a trick here and expand our equations of motion in this coupling function. Now, we can argue about whether or not that is sensible, but at least at zeroth order approximation, that's the approach I will take. So if I do that, what I find at zeroth order in this epsilon is just the dimensionless version of this coupling parameter. At zeroth order, what I get is essentially just Einstein's equations coupled to a massless scalar field. Since I'm interested in black holes, what I will say, okay, even if I would put a scalar perturbation on them, they will decay exponentially, they will die off. So let me make that explicit. And just at zeroth order, my solution is some kind of metric in general relativity and a zero scalar field. And now what you will see if you go then to next order is the following, is that our Einstein tensor really just becomes an operator acting on our first order metric being 0. And our scalar field at first order acted on it with a background wave operator and sourced by the background Gauss-Bonnet invariant. So just sourced by the background curvature. And that's something that we can evolve. So you see here, so actually here I make also the solution that first order metric is 0 explicit, and we can evolve that scalar field on top of our background, and that's the simulation that you will see in a moment. But let me just go to second order here. If we continue this exercise, you will see that at second order we again have an operator, or an Einstein operator, acting on the second order metric. And the source terms now, instead of being this ugly second derivative terms at the same order, are now computed only from the background metric and our first order scalar field. So none of these nasty second derivative square terms enter at the same order. And likewise for the scalar field at second order, we have again the box operator from the background and a source that also comes only from lower orders. So let me pause here for a second and let you look at this for a minute. Because what's the beauty, whether or not we believe in this effective field theory approach is one thing, but what the beauty is here is that at each order we essentially get the Einstein tensor that we know how to make well-posed with the right gauge choice, and a wave operator acting on our scalar field, and all the other terms are shuffled into being source terms, so they will not ruin our PDE properties at that particular order. And that's actually quite nice, and that's something that we can straightforwardly implement. And I dare say that if you have an effective field theory type expansion of what I just described, you're probably able to write them down in exactly that way. So in some sense, if you want to think about something that's not just a specific theory, that's probably the closest we can get in parametrizing, and very much quotation marks, numerical relativity. I think I will skip my note of what other approaches we might take, because I think that's just too much information. And let me just go to our simulations here. And before I show that to you, let me just mention one more thing. So I just showed you that the wave equation for the scalar field is sourced by the background curvature. So you can imagine that if I have a black hole, which is curvature, quite naturally a scalar field will be sourced. And actually people have shown that more rigorously and say that black holes have scalar hair, which means they have a non-trivial scalar profile really sourced by that background curvature. Now, one of the features that you can now think of is what happens if I have a binary thereof. So we have one black hole with a monopole scalar charge, and we take a second one with a monopole scalar charge and let them orbit around each other. And as you may guess, what we will see is actually scalar dipole radiation. And that's what I'm going to show you now in the animation. So I'm not going to go into any of the details of the implementation. And, oops, open. So what we're seeing here is a equatorial slice of the system. In the background, I have two black holes, one twice as massive as the other. And what we're looking at here is not the black hole spacetime itself, but the scalar field that evolves on top of that black hole spacetime. And here in the middle, we are already seeing these bulges, which is essentially the scalar monopole charge associated to each of the black holes. And if you look very carefully, you should see scalar dipole radiation now being emitted, becomes stronger and stronger as we go towards the merger, really leading to, yeah, we're close to merger now. So now you're seeing a relatively strong signal leading to a burst of scalar radiation going out, and our final scalar field will adjust to the background black hole geometry, which is just a single rotating black hole, and it will adjust to the scalar profile that you would expect for a single rotating black hole in this context. Now let me just say in a few words what we can do with these results, because what you can imagine now is that well, let me start the other way around. So remember, in the very beginning I said, okay, if you have two black holes in general relativity, they orbit around each other and they dissipate energy in form of gravitational waves. Of course, the same thing happens here, but now we are also emitting energy in form of scalar radiation. So we are emitting more energy for the same type of system. So what will happen is that a black hole binary in one of these theories would inspiral faster as compared to general relativity. And of course, the orbital frequencies directly translate modulo a factor of 2 into our gravitational wave frequency. So even though at this stage I haven't evolved the second order metric yet, so I haven't explicitly evolved any of the metric changes, we can already infer what the effect would be, because we know that there will be a phase shift due to the scalar radiation. And that's one of the calculations that we have done, and that then helped us to compare back of the envelope against LIGO observations. Let me just see. So now I'm doing what I usually don't like to do. I'm just skipping a few slides. And this is also a very busy plot, so I'm not going to show that to you. And let me just make some final remarks, because I structured all these things as kind of a play. And now, of course, even though we are not quite there yet and we haven't done the full exercise yet, the question is, once we've done that, will we have a drama with a lot of deaths, as usual in Shakespeare dramas, meaning that maybe a lot of theories will be killed off, which is probably what most people would hope for? Or is it a comedy, meaning they survive, or whatever other happy ending you can think of? So in order to do that, I hoped I convinced you that we can use gravitational waves as a new observational channel to infer those properties. And we need really the modeling of gravitational waves, at least in some proof of principle examples and some series, to be able to make or take those conclusions. I showed you a specific example where we had higher curvature corrections in our theory and first simulation. So the next steps really are to try and construct complete waveforms, which we are currently, well, at least to this order, doing with Cisco Jimenez and Leonardo Gualtieri. And one of the other ideas is, and I think Masha is also pushing that forward actually, where we try to see whether we can go towards numerical relativity and using our information either from specific series or these parameterized models to inform parameterized model building, which I think is probably the more efficient way to go. Okay, thank you very much. Yes. No. No. So in this case, so in this particular case, it's slightly different. So if you say, okay, my underlying theory is some high-dimensional model of gravity, and I reduce it down to 4 dimensions, then I will what's called a dilaton field, so a scalar field that essentially just measures the size of your extra dimensions. So it's not something that I would make up ad hoc, at least in this context, right? From the field equations, yeah. So in this particular context, I mean, it always depends on what you're asking about. I mean, it's also true that, especially if you're trying to explain behavior at large-scale structures, so cosmological models, I think there was a phase where people came up with using scalar fields as something to model. But I would guess that now that, or I would think that now it's at this somewhat more solid ground.
You said something like it's kind of better being Is that coming from mathematical considerations?
So this is if you write down the Lagrangian that I did, that's the field equations that you get to leading order. I mean, they are more complicated, but this is a leading order structure. So so that's what I was trying to say. So if you have, so again, 2 approaches, right? So let's. Yeah. So we are talking about the scalar corresponding, and so I think I will take the following approach. Let's write down a theory of gravity in d dimensions, and let's generalize it such that our field equations are still second order. So let's try and write down all the terms that we can think of that still give us second order field equations in arbitrary dimensions. So in 4 dimensions, if you do that, you end up with just the Einstein-Hilbert action. If you do that in 5 dimensions, you see that you actually can have this Gauss-Bonnet term, which is this particular Riemann squared combination. Okay, so let's stick to 5 dimensions. Now I say, wait a second, I live in 4 dimensions, I want to test things in 4 dimensions. So why don't I do a dimensional reduction? So why don't I go reduce it down by symmetry from 5 to 4 dimensions? If you do that, you essentially have a compactification. You have to somehow compactify your extra dimension in that sense, and that's parameterized by the scalar field phi. So this is one way to think of it. Yeah, is that a bit clear? So, but this is for this particular theory. So that's one way to get it.
So I guess if there's no more questions, let's